So this is the schematic editor window. This is the schematic editor window. So here we need to draw a schematic. Okay. First for inverter, we need two transistor lines, right? One is PMOS transistor and one is NMOS transistor. And these two transistors, from which technology node we have to take? ZPDK 45. Why? Because I have attached my library to ZPDK 45 nanometer. So that's why we should take the transistor from ZPDK. First method is we can go to create, we can select instance. First method, we can go to create, we can select instance.
Sir, your screen is not visible, sir.
Okay, sir. Okay. 1 second, sir. Okay, now, sir, is it visible to you?
Yeah, now it's visible, sir. Thank you.
Okay, sir. Thank you. So here we can go to create, we can select instance. So that is the first method. And second method is we have transistor icon. See my cursor, this one. We can directly click on this icon. That is the second method. Third method is shortcut key I. In your keyboard, shortcut key I. I for instance. So go to instance. To take the transistors, we need to go to add instance window. Here, browse. See here, now we should take the transistors from GPDK 45, right? So here select GPDK 45. So in the middle, if you scroll down, you can see the transistors. The NMOS, these are the NMOS transistors. NMOS 1V, NMOS 1V underscore 3, NMOS 1V underscore HVT, underscore LVT. So these are the types of transistors. LVT is low threshold voltage transistors. HVT is high threshold voltage transistors. So if you scroll down, you can see the PMOS transistors also. The PMOS 1V, PMOS, HVT, PMOS, LVT like that. So to see the full information of these transistors, so Cadence is giving one reference manual also regarding these PDK files. So same, earlier we had gone right. The path, go to places, Cadence tools, go to places, computer. So here go to home, in home install folder, right? Go to install. So install folder, we have one file, Foundry. So this is the Foundry file, PDK file. So go to Foundry. So in Foundry, so if you want to see the reference manual in analog, you can go to analog or digital. Both are there. So you can select respected folder. Here you can see 45 nanometer, 90 nanometer, or 180 nanometer. So okay, let's go 45 nanometer. So here we have docs folder. Docs means documents folder. So here we have reference manual. See this one, reference manual. If you open this manual, so it will show with clear information NMOS 1V underscore HVT. So like that, it will show all the information of your transistors, capacitors, resistors, everything. So you can take as per your requirement. Okay. Right now, I am taking PMOS 1V. Okay, that is PMOS transistor. Select PMOS 1V, close, here, close, here, hide. See here, if you want to change, you can change the width of the transistor. If you want to change here, total width 120 nanometer. If you want to change, you can change. Okay, so hide. Here, see, this is the transistor. You can see near to our cursor. To place the transistor, you can give left click, it will place. That is the PMOS transistor. Now we require NMOS transistor, right? So same procedure. Again, go to instance. That is shortcut key I for instance. Okay. Browse. Now select NMOS transistor. Roll up. So there you can see NMOS transistor. Close, hide, and place below to the PMOS transistor. So now I have taken two transistors. Now we require pins, right? Input pins and output pin. Okay, so here VDD and VSS. VDD and VSS also input pins, right? See, here we can take all the pins at a time. For example, see VIN, input pin, VDD pin, VSS pin. VDD means power, VSS means ground. So I am taking these three pins at a time. But we should not take output pin along these pins. Why? Because input pins should have the direction input, output pin should have the direction output. For example, I will show you. Now I want to take pins. Okay, so pins also we can take by three methods. First one, we can go to create, we can select pin. That is the first method. This is the first method. Second method, here we have pin icon. This is the pin icon. You can directly click on this icon, or else shortcut key P. A shortcut key P you can use P for pin. So here name. Second option, direction. So input. So input pins we should take at a time. For output pins, we should give the direction as output here. Direction we need to change for inputs and output. Okay, first I am taking input pins. So for input pin I am taking the name V. So if you want, you can take A also. A or B or C, any name you can take. So after giving the input pin name, give space. Now you can add second pin, that is VDD. So VSS also I am taking here only, space VSS. Okay, just give space in between them. So like this, you can take n pins at the same time. Now you see, here I am taking three pins, height. Now first VIN pin we can able to see near to your cursor. So after placing this pin, we can see the second pin. See, here I am placing input pin left hand side. Now we can see VDD pin. See, VDD we need at top side, right? VDD means power. See, if you want, you can rotate also. Your pins or transistors, anything. You can rotate. So for rotating R, you can use R key. See, here I am pressing R continuously. It is rotating. Okay, like this. You can place. Okay, so after placing VDD pin, now we can see VSS pin. Like this. So now I have placed all the pins, three input pins. One input pin and two power pin, that is VDD and ground pin. Now I need output pin. Same procedure, just change the direction to output. That's it. Again, go to P, create pin window. That is, you can use shortcut key P. Here I am taking the output pin name V out. So if you want, you can take Y or Z or X. Okay, any name you can take. So direction should be output for output pins. That is must and should. Hide and place here. And you can use F for fitting. It will fit to the window. It will come in the middle. Now wiring. You know, right? See here, I am zooming this one. See, this is the PMOS transistor. See, you know, right? The terminal, source, gate, and body terminals. Hello. Hello. Excuse me. Someone has turned on the mic. Can you please mute by yourself? Or else, if you want to ask anything, you can ask. Okay. Thank you. See here. This is the PMOS transistor. So the pin, the terminal which has the arrow symbol, that is source. This is the gate, and this is the drain, and this middle one is the body terminal, like a substrate. Same for NMOS also. So which has the arrow symbol. This is the source, and this is the gate, and this is the drain, and this is the body terminal, middle one. So here wiring also we can take by three methods. First we can go to create, we can select wire. That is first method. And second method, here wire icon is there. You can directly click on this wire icon, or else shortcut key W for wiring. Okay, now connect the source of PMOS to VDD. The source of PMOS to VDD. See, just to connect, for example, now I want to connect the source of NMOS to VSS.
Excuse
Okay.
me, sir.
So just give left click here.
Excuse me, sir. Hello. Hello, sir.
Hello.
Sir, the
No, sir, please
capital
tell.
letters, capital W, sir, small w, sir. Letters, sir.
Small, sir, small letters. Small
Small
W.
letter. Thank. Okay, sir. Okay, thank you.
Yes. Oh, okay, sir. Thank you. Okay. So here now I'm trying to connect the source of NMOS transistor to VSS. Okay. So give left click here on the source point. Move your cursor. Here again give left click. It will place. So like this you can give wiring. Both the gates. Okay, input pin to gate connection, and both the drains. Output pin to drain connection. So like this you can give the wiring for your schematic. And here you should remember one thing. You should connect the body terminal of PMOS transistor to VDD and the body terminal of NMOS transistor to VSS. Okay, this is the schematic of inverter. So like this you can connect NAND gate, OR gate, bigger designs. In any design you can connect like this. Now we need to save our design. See, to save our design, go to file. See, we have two options. One is save option. Second one is check and save option. Save and check and save. See here the difference is if you click on save option, it just saves your design. But if you click on check and save option, first it will check whether you have followed, you have given all the connections or not. Then only it will save. So that is the difference between save and check and save option. See, better to go with check and save option always. Why? Because if you miss any connection, here only it will show. For example, see here I am removing this connection, this output connection. Okay. See, to delete anything, you can use your cross mark here. See my cursor, this one. This is the cross mark. You can use this, or else you can use delete icon in your keyboard. Okay, as per your convenient, you can use. Now, cross symbol came near to your cursor. Now you can select whatever you want to delete. This is the procedure to delete anything, a transistor or pin or wire or anything. Now I'm clicking on check and save option. See, one warning. If you close this one, it will show with blinking. See, I'm zooming this one. See, it is showing with blinking, right? And I already told you, CAW window, command interpreter window will show you clearly about the errors or warnings. So this is the command interpreter window. See here, if you observe here, warning pin V out floating input. Pin V out floating input. That means output pin did not connected. We did not give a connection for output. So like this, you can check errors or warnings. Okay. Again, I'm giving wiring. Now again check and save. Check and save. Now I have 0 warnings or 0 errors. So here also it will you can check if you want. Schematic check completed with no errors. And inverter INV schematic saved. So inverter means our library name, INV means our cell name, schematic is our view, saved. So like this you can check. So with this step, schematic entry completed. Okay, again I'm repeating. See, for example, if I miss this connection, okay, I did not given this connection. So go to file, check and save. Check and save. See here I have one warning. And so here if you observe, the tool is showing with blinking. See, output pin is blinking, right? So there we have an error or warning. Now if you open the VSS main window, that is CAW window, here it will show clearly pin V out floating input. Pin V out floating input. That means output pin we did not connected. See, here we did not connected. So now you can again connect output pin to here drain connection. Now again you can go to file, click on check and save option. Now if you open CAW window, here you can see schematic check completed with no errors. Okay, clear? Okay, now schematic entry completed. See, if you want, you can simulate the schematic also. You can see the waveforms, or else you can create symbol for your design also, for your schematic. Okay. See, the advantage of creating the symbol is, for example, now we are designing inverter only. So inverter we require 2 transistors. We can easily take 2 transistors and we can easily give the wiring and we can easily see the simulation results for inverter. But if you take the bigger designs, let's say the design which needs 20 inverters, and let's say the design which needs 20 inverters. So at that time we require 40 transistors, right? So 40 transistors we should take, and 40 transistors, it's a little bit difficult to take 40 transistors. So instead of taking 40 transistors, first we can create one schematic for an inverter. So we can create the symbol for it, and we can take that symbol 40 times or 20 times. So this is very easy to create the symbol. And here, how to create a symbol. So here to create the symbol, we can go to create cell view from cell view. Create cell view from cell view. So one pop-up window open here. So here just cross check with your library name and cell name. So our library name and our cell name should be there here, inverter INB. So if both are correct, click on OK. So here it is asking symbol generation options. For example, the tool is asking at which side you want your pins for your symbol. For example, if you need all the pins, that is input pin, output pin, VDD and VSS pin, all the pins in left hand side. So here you should mention all the pin names in left pins here. So if you want right hand side, you should mention in right pins. So like that, the tool is asking the symbol generation options. Okay. And here you remember one more point. These are case sensitive. For example, if you use the names of the pins in small letters in your schematic. See, we should not give here in capital letters in symbol generation options. These are case sensitive. Okay. So here and here I am taking my pins as per the schematic. As per the schematic. So that's why I'm taking left pin V in pin only, left pins V in, right pins V out, top pin VDD, and bottom pin VSS. So as per my schematic only, here I am taking the pin names. That is V in, V out, VDD, VSS. Click on OK. Now, please give me 1 minute time. Okay, so this is our symbol. This is my symbol for inverter. And here this red color rectangular line. So this is the IO boundary, that is input output boundary. So no need of this one. You can delete this one IO boundary. And instance name also you can delete. And this part name you can delete. Either you can delete or you can give name also. So give double click, the editor option will enable. So give the name inverter. So like this you can save your symbol. See, in any shape you can save your symbol. Why? Because we already drawn the schematic here. So if you run the symbol, this one, it will take the operation of the schematic only. Here creating symbol means what? As per your requirement. You are giving one shape for your schematic, that's it. In a single line also you can create your symbol, or in any shape you can create your symbol. We already fixed in our minds, like inverter symbol first has one buffer and at the end one bubble, right? One circle. In that shape also you can create. I will show you. So for that, this one also not required. So to create your symbol, here we have some icons. See my cursor, this one, create circle. If you place the cursor on that icon, you can see the names also. Create circle, and then create polygon, and create ellipse, and then create line, and create arc. So these are the shapes. By using these icons, you can create in any shape. See, first we need buffer, right? So take create line option. So I am creating one buffer icon. See, buffer symbol. So like this, you can draw in any shape. So buffer. Now at the end, we require circle, right? So now here take create circle, draw the circle here like this. And if you want, you can move your names. You can drag wheel name. If you, I'm placing here, and this line I'm placing here. See, these are not mandatory. You can save in any shape. So, so symbol creation done. Now you can check and save. Here also go to file, click on check and save icon.
Excuse me, sir.
So here also I have
Hello. Excuse me, sir.
hello.
Sir, VIN ఒకవేళ ఆల్మోస్ట్ డిలీట్ అయిపోతే హౌ ఇట్ పాసిబుల్ రీకనెక్షన్ సార్ VIN ఆర్ VOUT
Yes, sir. Yes.
ఒకవేళ ఆటోమేటిక్గా డిలీట్
If you
చేయడం yes.
Yes, sir. So by for example, if you delete by mistake anything, we have undo and redo options, sir. Here, see my cursor.
ఓకే ఓకే సార్
So this is the undo, and this is the redo.
ఓకే
So by using those two options, we can get, sir.
థ్యాంక్ యూ సార్ థ్యాంక్ యూ సార్
Okay, sir. Okay. So file, check and save. So here also you can check in CIW window. What is the main window? Cross view check completed with no errors. Now symbol completed. So after saving your symbol, you can close this symbol also. Now open your library manager. By default, it's you already opened. You minimized. So from bottom side, you can open library manager window. So here, see, this is our library name, right? Inverter. And this is our cell name, INV. These are our views, schematic and symbol. So first we have created schematic and then symbol. Okay. Now, see, to see the simulation for our symbol, again we need to open cell view window. In that cell view window, we need to take our symbol. So to that symbol, we need to add supply voltage, input voltage, ground pins, output pin. So we need to run the simulation. So here just we need to test our symbol. That's it. So for that, again, go to file, new, cell view. Cell view. So here cell name INV has already taken. So here I'm just giving some different name, underscore test. So without space, you can take any name. So now we are testing our symbol. That's why I've taken INV underscore test. So like that, you can take any name. Click on OK. So this is the new schematic editor window. So in this window, we need to take our symbol. So we need to add the supply voltages, everything to that symbol to see the simulation results. Same path. Again, go to instance, browse. See, now I'm trying to take our symbol, right? So our symbol, where it is placed? Our library. So that is inverter. This one. Inverter. And where it is placed, the cell name INV, right? INV. So here you can check symbol. See, for transistors, we had gone for ZPDK 45. For our symbol, we should go to our library name. Close, hide, and place here. So now we need to add supply voltage, input voltage, ground pins, ground terminal, and output pin. So here supply voltage, input voltage, ground terminals, everything we should get from analog library. So I will show you. So go to instance, browse. So here you can see analog lib, this one, analog lib. And see here supply voltage means VDC, right? VDC. the constant supply voltage we are taking. So that is VDC, close. See here we should mention the DC voltage. So DC voltage. And here you remember these 3 points. So here I am telling the voltage ranges for technology nodes. See, for 45 nanometers technology, we can take the supply voltage range from 0.45 volts to 3.3 volts. See, up to 5 volts we can take, but while coming the concept wise after 3.3, some cutoff region, some regions will be there, right? Before 3.3 only active region, right? So that's why I'm telling the supply voltage range from 0.45 to 3.3 volts for 45 nanometer. For 90 nanometer, the range is 0.9 volts to 3.3 volts. For 90 nanometer, the supply voltage range is 0.9 volts to 3.3 volts. For 180 nanometer, 1.8 volts to 3.3 volts. 1.8 to 3.3. So in between, you can take any value. Now we are doing in 45 nanometers technology. So that's why we can take supply voltage from 0.45 to 3.3, any value. So, okay, we will go with lesser voltage only. So that's why I'm taking 0.45. So you here units no need to mention. By default, it will take. Just give the value. That's it. So 0.45. Right? So this is the VDC. VDC means power, right? So we needed VDD. So you can rotate if you want. You can press R. It will rotate. Or else here rotate. Okay, R. And if you want, you can drag also near to VDD. And if you observe, VDC has two terminals. One is positive terminal and second one is negative terminal. See here, positive terminal means we should connect to VDD. Negative means ground. Okay. Now, input voltage. So again, go to instance, browse. So here search for V pulse. V pulse. See, for example, if you want your waveforms in a pulses, so here we should take V pulse. If you want your waveforms in a sinusoidal wave, so we should take here V sine. So as per your requirement, you can take anything. So now we are doing inverter design. So we need pulses. That's why I'm taking V pulse here. Close. So here also DC voltage. DC voltage already we have taken. Here also we can mention that is 0.45. Now voltage 2. Voltage 2 also we should give supply voltage only. Why? Because here we are giving pulses. See, pulses means what? Initially it is 0. After sometimes it will go high. 0 to 1, 1 to 0, 0 to 1, 1 to 0. So this is the pulses, right? So that's why I'm taking voltage 1 as 0, voltage 2 as supply voltage. That is 1. Next, time period. Here period means time period. See, actually time period we should take based on frequency only. For example, let's say if you want a design inverter with frequency 500 megahertz. So we can convert it into time period, right? F equal to 1 by T. So we will get, I think, 20 nanoseconds or something, I guess. So like that, based on frequency only, we should take the time period here. So right now we don't have any frequency value. That's why I'm taking here by default 4U. 4U means 4 micro units or seconds. If you want in nanoseconds, you can take 10N, 10 nano, 100N, 100 nano, 100U, 100 micro, like that. Right now I'm taking 4U by some value. Next one, delay time, rise time, fall time. These are not mandatory. If you want, you can take, you can mention 1 picoseconds, 2 picoseconds, like that. Next one, pulse width. pulse width, you can take half of the time period value for 50% duty cycle. You know, right? Pulse width means what? The on time, right? On time of the pulse. So if you mention the 50% value here means that is 50% duty cycle. So based on your requirement, you can take and height and place here. So here also same. Positive terminal means input symbol, negative means ground. So now we need ground, right? So again go to instance, browse. Here search for GND. GND means ground. Ground, close, height. Here we require 3 grounds, right? One for VSS, one for SS, one for V pulse negative terminal, and another one for VDC negative terminal. See here you can take 3 ground terminals, or else you can take 1 ground terminal, we can connect through wiring. That is your wish. So here I am taking 3 ground terminals. See here, if you observe here, for V pulse and VDC, I have connected the ground on the point. See, here I will show you. See, I have connected the ground terminal on the point here, but here I did not connect it on the point. Why? Because see, if you place the cursor on your symbol, so it is showing one yellow color border, right? So that is IO boundary. So we should not place outer terminals inside of that boundary. For example, if you place this ground terminal like this, so you will get error. Why? Because we should not place outer terminals inside of that boundary. That is IO boundary. So that's why here I have given some space. Clear this point. Now take wiring and connect the input of our symbol to V pulse positive terminal, the VDD to VDC positive terminal, and VSS to ground. Now we require output pin, right? So again go to pin, take output pin name, direction also output, right? For output pin, height and place here. And again take wiring, connect output pin to output symbol. So clear? So this is our schematic. Now again go to file, check and save. Now schematic completed. Now simulation. To run the simulation, go to launch ADEL. Here ADE means analog design environment. Analog design environment. So here first go to analysis, choose. See here stop time. Stop time we should give greater than or equal to time period value. For example, time period we have taken 4 microseconds, right? So we can take either 4 microseconds or more than 4 microseconds. But we should not take less than 4 microseconds. That is the condition here. So here I am taking 8U or 10U, 20U. Any value you can take more than that. Then select moderate, click on OK. Now we need to plot output waveforms, right? For input and output. So for that, go to outputs, to be plotted, select on design. So now we require input and output waveforms, right? So select on the wires, not on the terminals. So this is the input wire. So select on input wire and output wire. So that means we are plotting those waveforms. So again come to ADL window. Now run the simulation. So this is the run icon. Run the simulation. So these are the waveforms. To split those waveforms, we have one icon here, split all stripes, this one. So now you can check. It is inverting. So with this step, simulation completed. Now layout. So here see this ADL window session we can save our state. For example, if tomorrow or day after tomorrow, if you want to run again the simulation, no need to do this analysis and this plotting. Okay, you can now save your state. Later we can load that state. I will show you how to load that state. So to save the state, go to session, save state. Here select cell view. Cell view. So here state by default it will come. Click on OK. Now the state of ADL window saved. Now you can close this one also. And now we will start the layout. And you remember one more point, to draw the layout, we should not use these terminals, VPulse, VDC, ground terminals. Why? Because we should not import these terminals onto the layout window. So we have to use this schematic. To draw the layout, we have to open the schematic with transistors and pins. So from here, go to launch, layout Excel. So to draw the layout, we need to open this window, layout Excel. So here, create new automatic. Just cross check with it. Click on OK. Here also give OK. Just cross check with your library name and cell name. Our library name and our cell name should be there. Click on OK. Okay. So by default, it's open. This is the layout editor window. This is the layout editor window. See, first we need to generate our components from schematic, right? That means our transistors and pins. So go to connectivity, generate all from source. Go to connectivity, generate all from source. See here, just cross check this checkbox. In boundary should be selected always. Just cross check with it. Click on OK. See, these are the transistors and pins. See, in our schematic, we can able to see this source, gate, drain, body terminals, right? For PMOS and NMOS. So here also, if you want to see the terminals, in the terminals, press Shift F. Shift F. So if you zoom, see here, yes, yes means source. So this is the source. Here D means drain. So this is the drain. Here green colored one. G means gate. Same for NMOS also. This S means source. G means gate. D means drain. And this V out means output pin. V in means input pin. This is VDD. And this is VSS. And if you observe here, we are not able to see the body terminals, right? So here we can able to see the body terminal here in the schematic. But here we are not able to see the body terminals. So to see the body terminals, first select PMOS transistor, press Q. Q for properties. Here go to parameter, body tie type integrated. So we have two types of body tie types. One is integrated, second one is detached. I will show you the difference between integrated and detached. So for PMOS I am taking integrated. Click on OK. Now for NMOS I am taking detached. For NMOS I am taking detached. See here, this is the PMOS. See, integrated means what? Here earlier this is the source, right? This is the source. This is the body terminal. So here integrated means what? The source and body terminal both are attached. If you take NMOS transistor, here we have taken detached, right? Here see this is the source, this is the body terminal, both are separated. So integrated means both are attached, detached means both are separated. So this is the difference between integrated and detached. As per your requirement, we should take either integrated or detached. So for inverter, we need integrated only for the two transistors. So that's why I'm taking NMOS also integrated. Okay, so this is the PR boundary. This is the PR boundary, this border. So PR boundary means placement and routing boundary. So we should, if you take n number of transistors or pins, that is 20 transistors, 40 transistors, we should place inside of this boundary always. See, to calculate area, here why we are doing layout? To calculate area, right? So to calculate area, this PR boundary must and should. So without this PR boundary, we cannot calculate the area. So if you want, you can if you want to stretch, you can stretch this PR boundary. For example, if this space is not enough for your transistors, you can stretch if you want. So to stretch, press S. Yes, and here we should not stretch from left side or down side. This is like an axis. You can stretch from top side or right side. So press S. Now stretch symbol you can see near to your cursor. Now you can select whatever you want to stretch. Now I am trying to stretch from top side. So that's why I'm selecting top one. Give left click. You can move your cursor or upper arrow key. Again give left click. It will place. Now right side also. So like this we can stretch our PR boundary. And this is the now power rails. We did in VSS rails. See, to connect the terminals, we need power rails, right? We did in VSS rails. So to create the power rails, first select the VDD pin, give right click, pin placement. So VDD rail, we need a top side, right? So that's why here I'm selecting the edge as top. Here, top, apply, H rail. H rail means horizontal rail. Now same VSS also. Now here select VSS. So VSS we needed bottom edge, right? So give edge as bottom, apply, H rail. Now if you close this one, we can see the power rails, VDD and VSS rails. See, this is the VDD rail and this is the VSS rail. Now you can drag your transistors. Say you can select, click on and hold. You can move your transistors like this. And you can move your pins also if you want. I'm placing in a proper manner. That's it. Now we should give paths. See, by using schematic only, we should give paths in the layout. And here you remember 2 points. Here to connect other than the gate, for everything. For example, for VDD connection, for VSS connection, for drain connection, source and body terminals, input pin, output pin, for every connection other than the gate. I already told you in the layout stage we are going to use some metal layers to give paths, right? So in left hand side you can check, these are the metal layers. So other than the gate, for every connection we should take metal 1 layer. So if you scroll down you can see metal 1. So this is the metal 1. For gate connection, we should take poly. So this is the poly. So these are the metal layers. Now open your schematic. See here, the source of PMOS transistor connected to VDD, and the body terminal of PMOS also connected to VDD, right? Source is connected to VDD, body terminal also connected to VDD. And here source and body terminal, we should take metal one layer, right? So come to layout window. So here shortcut key P for paths. So now I'm trying to the source and body terminal of PMOS transfer to VDD. So that's why here I'm taking metal one. Select metal one here. Connect. Same like our wiring. In schematic level we have used, right? Now again go to schematic. Now same here for NMOS also. The source of NMOS transistor connected to VSS. The body terminal of NMOS also connected to VSS. So again come to layout, connect both the source and body terminal of NMOS transistor to VSS. Now again come to the schematic. The drain of PMOS transistor connected to the drain of NMOS. So this is the drain of PMOS transistor. So we should connect to the drain of NMOS. Now the output pin to drain connection, right? So again come to layout window. So this is the output pin. So connect the output pin to drain connection. And now see both the gates. See for gate connection, which metal layer we have to take? Poly, right? So here take poly, connect both the gates. See here we should give line alignment. See we should connect like this. See we should connect like this, line alignment. For example, if you connect like this, see misalignment is there. I will show you the type of error also. So that's why I'm connecting like this. Okay. Now again open your schematic. Hello, is it visible to you, sir? Yes.
Yes, sir. Yes, sir.
Okay, sir.
Yes, sir.
Okay, sir. So here now input pin is connected to gate connection, right? So open the layout. But here if you observe, input pin is metal one layer, gate is poly. Here we should not connect two different metal layers. We should not connect two different metal layers. So in this case, we should take via. I will show you how to take via. See, now we are trying to connect this input pin to gate connection, right? So input pin metal one. So take metal one first. So take metal one. Give path to input pin. Move some distance. Now press space bar in your keyboard. Space. Press space bar. So this is the select via window. So now we require polymetal layer, right? So here select poly. Polymetal layer. Close. So this is the via. This is the via. So after placing this via, the polymetal layer will come. See here. Now here I am placing the via. Now the polymetal layer will come. Connect it to gate. So like this we should connect two different metal layers. Okay. So with this step, layout completed. You can save your layout. So go to file. You can save. Now next one, physical verification.
Screen sharing is
physical
stopped, sir.
verification.
Screen sharing is
Sir,
stopped,
is it
sir.
stopped, sir?
Yes, yes.
Sir, can you please check once, sir? Actually, it is
Okay,
coming.
sir. Is it
I'm
visible,
checking.
sir?
It is
Visible, sir.
visible.
Yes, sir. Yes. Okay, sir. Sir, please check your internet connection, sir, once.
Okay.
Okay, sir. So here, before going to physical verification, first we need to select our rule file. For example, if you run DRC, which rules the tool will execute? So now we are doing 45 nanometers technology node, right? So first we need to add our rule file of 45 nanometers technology. Okay. So go to Ashura here. Here, go to Ashura technology. Technology. So click on the three dots here. See here, if you give double click on the two dots, we can go back. Where we should go? I already told you, in home, install folder is there, in install foundry is there, in foundry analog 45 nanometers. So earlier I have shown you, right? For reference manual. Same path we should go. So go back to install folder. So go to install folder, then foundry, then analog. Now we are doing 45 nanometers, right? So go to 45 nanometer. So in right hand side, you can see Ashura underscore tech.lib. So this is the technology file, rule file. So give double click on this file. So here also you can check that file added, click on OK. Now first one DRC, right? In physical verification, first one DRC. So the tool name is Ashura, right? So go to Ashura here. Ashura, run DRC. Run DRC. So here give run name. Run name. Run name without space you can take any name. So I am taking DRC here. Run name. So technology. Just now we have added right technology file. Just now we have added. So select the technology GPDK 45. Now click on OK. These two changes only we have to do. Click on OK. Here also give OK. Here give S. Do you want to view the results of this run? Give S. See here I have 4 errors. So we need to rectify these 4 errors. See here first error is what? Minimum envelope width. Minimum envelope width greater than or equal to 0.3 micrometers. So the width of the envelope we have given less than 0.3 micrometer. So we need to increase the width of the envelope, right? And where it is happened exactly? To see the place, so select this arrow symbol, arrow mark. So it will show with blinking. See, it is blinking, right? So that is the envelope. That envelope width we should increase right now. So in left hand side, select envelope metal layer. So that is a rectangular shape, right? Envelope is in a rectangular shape. So we should increase in a rectangular shape only. So here select envelope. So go to create shape rectangle. So I am increasing rectangular shape only. That's why I'm going to create shape rectangle. So just increasing the width of the envelope in a rectangular shape. Okay, so that's why I have increased in rectangular shape only. So I save your design layout. Again go to Ashura, run DRC. So I already given run name and technology file. Click on OK. Here it is asking for overwriting. Give OK. Here give S. See now I have 2 errors. See, one error is minimum poly interconnect width greater than or equal to 0.05 micrometers. Where it is happened? See here. I did not given proper connection. It is blinking. See this one. So again, I'm removing this one. Again, I'm giving the poly metal layer. So again, save this one. Go to Ashura, run DRC, click on OK. See, now no DRC errors found. So I have no errors. So DRC completed successfully. Now next one, LVS. Layout versus schematic. So again go to Ashura, run LVS. Run LVS. So here same, give run name LVS and technology GPDK 45. Click on OK. Now here you see schematic and layout match. Schematic and layout matched and total DRC violation 0. 0 cells of 0 net mismatches, device mismatches also 0. So everything successful. LVS also completed successfully. Clear? So with this step, physical verification completed. Now next one, RC extraction. Next one, RC extraction. So again go to Ashura, run Quantus QRC. Run Quantus QRC. So here just cross check with your technology node, that is GPDK 45. So rule set, typical, not best, not worst. So I'm setting to typical and output extracted view. Now we are doing RC extraction, right? So output extracted view. Now come to second option, extraction option, this one. So now extraction type, we are doing RC extraction, right? So extraction type RC. RC. So ref node, reference node. See here, this name we should give with respect to ground. So here I have taken VSS, right? So take reference nodes VSS. This is also case sensitive. I have taken small VSS, that's why here also we should give small VSS. Next one, net listing. Net listing. So first option do not include. Second option include as comment. Third option also do not include. Fourth option also include as comment. So here click on OK. Here also give OK. Okay. Here you see the Quantus QRC run LVS completed successfully. So you can close this one. So open your library manager. So here in right hand side you can check AV extracted. So give double click on that one. So zoom it. To see the transistors and resistors and capacitors, press Shift F. Shift F. So now you can see resistors and capacitors. See resistor, capacitors. So like this you can check. Okay, so this is the RC extraction. So with this step, RC extraction also completed. Now next one, post layout simulation, that is back annotation. So again we need to run the simulation. So come to library manager window. go to File, New, Cell View. Cell View. Here type should be config. Here type should be config for post layout simulation. Config. Click on OK. See earlier for which cell name we have generated simulation results, INV underscore test, right? Cell name. Okay, cell name INV underscore test, right? So select the cell name INV underscore test. So for that same cell only we should run the simulation results, post layout simulation. That's why I'm selecting cell name INV underscore test. Here view schematic. View schematic. Now select use template. Use template. Here I already told you for simulation the tool name we are using Spectre, right? Someone turn on the mic, ma'am. Can you please mute by yourself? Yes, ma'am. Thank you. So name Spectre, right? The tool name. So here select the name Spectre. Spectre. Click on OK. So here also give OK. So this is the new configuration window. Here select the tree view. We have two views. One is table view. Next one is tree view. So this is our design folder icon. This one. This is our design. You right click. Set instance view. AB extracted. See here just we are reopening our design with RC extraction. That's it. AB extracted. Save and open. Open. So now the schematic open. This one. This is after RC extraction. So for this schematic again we need to run the simulation. Same procedure. Earlier we have done, right? Go to launch ADEL. So ADL window already saved, right? Our state already we have saved. So now we can load the state. So here go to session, load state. Go to session, load state. Here select cell view. See cell name INV underscore test, right? Select INV underscore test. So state by default it will come Spectre underscore state 1. That means we have saved our state. Click on OK. Now run the simulation. So now you can split your waveforms. So this is the post layout simulation. Now last one, GDS2 file generation. So this file come to main virtuoso window, that is CAW window. Go to file, export, stream. Go to file, export, stream. So here just we need to select, we need to give our design information. That's it. For example, see library. So we should select our library name, that is inverter, cell name, INV, view, layout. Click on OK. Stream file. Just click on the three dots. Save. So it just show the file name path. Say inv.gds. The GDS2 file extension is .gds. So that file will place in home, ntuple, desktop, inverter, inv.gds. So it just give the file path. Next one,
Excuse me,
technology
sir.
library. Yes, sir.
Excuse
Yes.
me, sir. So what is GDS, sir?
Sir, the abbreviation is Graphical Data Stream Information Interchange, sir. GDSII.
Okay, thank you.
Okay, we can call it as GDS2. So to fabricate your IC, for example, if you want to fabricate this inverter design, we need to generate this file, GDS file. We need to send this file to fabrication companies, sir.
Okay, sir.
Yes, sir. We can also call it a tape out file, sir. I think you heard this name, sir, tape out file.
Yeah, sir.
Okay. So now technology library. So technology library, now we are doing GPDK 45 technology, right? So select GPDK 45. Now translate. Translate. See, translation completed, 0 errors and 0 warnings found. Yes. So now if you open your work folder, inverter folder, there you can see inv.gds file. So this one. If you open this file also, see, it will open like this. So we are not able to understand also. Why? Because here we are exporting this file, GDS file. So fabrication people have that access to import this file and they can see the information. So this is the procedure of full custom IC design. So this is the entire procedure for full custom IC design. So tomorrow we will see the semi-custom IC design. See, tomorrow no need to do from transistor level. Okay, we can simply write one code. I will show you tomorrow the procedure of semi-custom IC design. So now, if you have any doubts, you can ask, sir, or you can put it in chat box.
Dear participants, if you have any query, you may ask.
Sir, from my side, one question, sir.
Yes, sir, please.
After before drawing the layout, we are taking only schematic of without VDD, VSS, VIN, and Vout. No, if we take with VS, VDD, and Vout, what is the problem, sir? Have you got my point, sir?
Sir, before layout also we have taken no, sir, VDD value.
No,
See here
that
VDC means VDD only, right?
okay, sir. But to create the layout, sir.
To create the layout, this schematic we have taken.
Yeah, sir. So we
Yeah, why? Because, sir, in the layout window, so it won't allow these terminals, sir. This VDC and VPulse terminals. It is only used for to generate the simulation results. That's it. Is it clear, sir? Your doubt?
yeah, okay, sir.
That's why we have opened this schematic. So it allows the pins and transistors.
Okay, sir.
Yes, sir.
Thank you.
Okay, thank you.
Participants, any other queries?
Shall can you provide this video, sir, recording video for us for practicing purpose?
Yes, sir. We are working on it. So if time allows, we will provide the recording session also.
Okay, thank you, Kiran Chand, sir.
Any doubts, sir?
So there are no query. I think we can conclude for today's session.
Thank you, sir. Nice section, sir. Thank you so much, sir. Kiran, sir.
Thank you, sir.
So, dear participants, tomorrow session will start the same time. We'll meet in the tomorrow session.
Please provide a manual link, sir.
Sure, sir. Sure, sir.
Thank you, sir. Thank you.
And one more thing, attendance form has been posted in the chat. So please provide attendance. Dear participants, please provide the attendance.
Sir, section is closed, sir.
Sudhir sir, thank you.
Okay, sir. Thank you, sir. Sir, tomorrow also same timing, no, sir? 6:50.
Same time, sir. Yes, sir.
Okay,
6:45.
sir. Okay.
7 we will start. Sir, thank you so much,
Okay,
sir.
sir. Thank you, sir.
Actually, I want to express my heartful gratitude from your insightful and engaging session, sir. and your expertise
Thank you
and
so much,
passion
sir.
shown through. Very well done, sir. And I truly appreciate the valuable knowledge you shared. Thank you for inspiring us and making the event so meaningful, sir. Thank you so much.
Thank you so much, sir. Thank you so much, sir.
Right, sir. Right, sir. Bye, sir.
Okay, sir. Bye, sir.
హలో
ఒక్క నిమిషం
నీకు కూడా ఉందా?
లేదు లేదు
నా ఫోన్ ఉందే.
ఆడపిల్లని లంజలని హర్ట్ చేయొచ్చు నీకు తెలుసు మరి మిమ్మల్ని హర్ట్ చేయాలంటే మన లంచొక్క అంటాను అక్కడ కూడా మీకు మేమే కావాల్సి వచ్చింది బూతుల్లో కూడా అమ్మని వాడుకుంటే కానీ జీకింత సెలవు మీకు పెట్టా ఫోను
ప్లీజ్ రా
మాట్లాడ ఇప్పుడు నేను ఎక్కడున్నాను తెలుసా తెలుసా
ఇంట్లో